Now that you've downloaded the flanker dataset, let's check the quality of the images. First, open a terminal and navigate to where you downloaded the flanker dataset. In my case, it's in the Downloads folder, and it's named this. Let's move it to the desktop using the move command. If you need to review how to use Unix, there are links in the More Info box down below. I'm going to move the dataset to my desktop and rename it Flanker. The data are organized in a standard format called BIDS, or Brain Imaging Data Structure. For example, within sub-08, there's an anatomical directory and a func directory. Within the anatomical directory, there's an anatomical image named sub-08T1W, and within the func directory, there are 2 runs of functional data. There are also TSV files for each run, indicating onset times for when each trial happened for each event, relative to the onset of the scanner. The first FSL command we're going to use is called fossilize. You can give it an argument or input, which automatically loads that image into memory and displays it. Type fossilize and then the name of the anatomical image and press enter. The first thing you'll notice is that the image seems a little dark. The contrast isn't very good. That's because certain blood vessels in this image are bright compared to their surroundings, and by default, everything else in the image is scaled relative to the brightest part of the image. To fix this, in the contrast window here, set the maximum to a lower number, such as 800, and press enter. Then click and drag the crosshairs around the image, noting how the viewing windows change, and getting a sense of how the image is organized into 3 dimensions. You should also check for artifacts such as Gibbs ringing, which looks like ripples in a pond. Check the link below for examples of other artifacts you may see in your data. Some artifacts are due to the subject moving too much, but others can indicate a problem with the scanner itself, which you should let the scan technician know about as soon as possible. Once you're done looking at that image, click on Overlay, Remove All to clear the windows, and then click on the Add from File button and navigate to the subject's func directory, selecting the first run of functional data. In a typical fMRI study, you collect a high-resolution anatomical image and lower-resolution functional images. Although, on this functional image, you can still identify certain features like the cerebellum and also the ventricles. The reason the resolution is lower in this image is that for the functional data, we're acquiring so many images at such a fast rate that we don't have enough time to collect high-resolution images for each volume. As with the anatomical image, you should check for artifacts, such as really bright spots in the white matter or really dark spots in the gray matter, and vice versa for the anatomical image. These can indicate a pathology that you should let the scan technician know about immediately. When you're done checking for artifacts, take a look at the time series, or the change in the images from volume to volume. A functional data set is 4-dimensional, meaning that it is a series of 3-dimensional volumes strung together. You can look through the time series by clicking on the up and down arrows next to the volume field. Or you can click on the movie reel icon, which will flip through the volumes like the pages of a book. Notice that the images seem to move a little bit, even though the subject is being quite still in this example. Some of the movement is because of blood pulsing through the arteries. Some of these voxels will change intensity slightly over time, which is normal. However, be on the lookout for any major jerking motions of the entire brain in any of the 3 windows. If you do see that, it may indicate that the subject doesn't have usable data. Later, we're going to be using a pre-processing step called motion correction to try to attenuate any of the motion artifacts. And it will also produce a report for you to make an objective cutoff for whether you want to remove or keep the subject. At this point, start to play around with the fossilized viewer, changing things like brightness, contrast, opacity, and even the color scale. As we continue with the course, you'll use more advanced features to check your data at each step along the way. This video will show you how to do all of the pre-processing steps on your computer. Before you continue, make sure you've already installed FSL and that you've downloaded the Flanker dataset. If you need help with either of those, see the links in the More info box down below. This tutorial is split into 3 shorter videos, one covering brain extraction and a brief introduction to the FSL data viewer, one showing you how to use FEAT, which does most of the pre-processing steps, and a final video demonstrating how to check the pre-processed images. Let's start with brain extraction. To begin, we need to remove the skull from our anatomical images. We do this for 2 reasons. 1, we're not interested in the skull and other non-brain areas. And 2, removing the skull will improve the alignment of the registration and normalization steps, which are discussed in the next video. First, navigate to the sub-08 directory of your Flanker dataset. When you're there, type FSL and press return. This opens the FSL Graphical User Interface, or GUI. The first button on the menu is BET Brain Extraction. Click on it, and notice that it opens up another window. Most of the FSL tools have a field for both the input image, which is the image we want to apply some process to, and an output image, which is the image that is created after the process is completed. Click on the folder icon to select an input image, and select the anatomical file in the ANAT directory. Click OK. Notice that this automatically fills in the output image field with the name of the input image and _brain appended to it. The input and output fields are required. BET won't work if the fields are empty. The other fields are options, which you can change if you want. Usually, it's best to leave the defaults alone. They've been selected because they give good results for most datasets. For now, click the Go button to run BET. When you see the word Finished in the terminal, you'll want to look at how BET changed the image, and you'll want to make sure there weren't any problems. Click on the Fossilize button at the bottom of the FSL menu. This opens up the FSL data viewer, which is useful for looking at data after each processing step. Click on File, Add from File, and then hold down Shift to select both the raw and the brain extracted image. Once they've loaded, set the max contrast to 800 for both images to produce the best contrast between the tissue types. Then in the Overlay List panel, highlight the brain extracted image and click on the up arrow next to it to make it overlay the original image. Then click on the contrast color bar and select blue, light blue. This highlights the brain extracted image and makes it easier to see what was removed from the original image. In this case, everything highlighted in blue is the brain extracted image. If you see any gray matter outside of the blue outline, that means brain tissue was removed by BET. If, on the other hand, you see bits of skull within the blue outline, that means some non-brain areas were not removed. Click and drag the crosshairs around the image to see whether too much brain was removed or whether too much skull remains. In this case, it looks like BET was too aggressive. For example, part of the frontal cortex is missing. Close the Fossilize window and go back to the BET window. Notice that the fractional intensity threshold controls how much brain is removed. A smaller number allows you to preserve more cortex at the risk of including more non-brain areas. Let's change this to 0.2 and change the output suffix to _FO2 to keep our files organized. Click Go, and when it finishes, open up Fossilize again. This time, we're going to load the raw image and the newest brain extracted image in the ENIGMA directory, and then do the same setup as we did previously. Remember to check all 3 viewing panes and to look around the edges of the brain for any problems. What do you think of this output? Is it better or worse than before? If you have to choose, I recommend using a lower threshold, even if that means keeping parts of the skull. For registration and normalization, it tends to be less problematic than the alternative. Once you've run BET on the anatomical image, you're ready to use FEAT, the fMRI expert analysis tool, which runs the remaining preprocessing steps. First, make sure you've opened up FSL from the sub-08 directory. Then click on the FEAT button to open the FEAT GUI. You'll notice that there are several tabs in this window, corresponding to different analysis steps. Since we want to focus only on preprocessing, click on the drop-down menu and select Preprocessing. This will gray out the Stats and Post-Stats tabs, which we will learn about in a later chapter. The first step is to load the functional data. Here, we'll be analyzing each run of functional data separately. Click on Select 4D Data, and then click on the folder icon to select the first functional run in the func directory. When you click OK, you'll notice that some of the fields are filled in automatically. The TR and the total volumes in the dataset are read from the image header. Make sure this matches up with the parameters you used to collect the data. If you aren't sure, ask your scan technician. The output directory will contain the results of the preprocessing. Let's call this Run 1. Leave the other options as they are. Again, ask your scan technician if there are any volumes at the beginning of the run that you need to discard, due to higher signal intensity in the first few images. In some cases, the scanner will automatically discard them for you. Now, let's click on the Prestats tab. There are several options here, but we're only going to focus on motion correction, slice timing correction, and spatial smoothing. High-pass filtering will be discussed when we get to modeling and statistics. And all you need to know about the BET brain extraction button here is that it does for the functional images what we did for the anatomical image. As you saw in the chapter on preprocessing, motion correction will undo any movements made by the subject during the scan. Slice timing correction is up to you. FSL's default is to not do it, and instead account for slice timing differences by including a temporal derivative, another concept that will be discussed in modeling and statistics. If you do decide to do slice timing correction, ask your scan technician what the ordering of the slices was. In general, it's best to leave the defaults as they are. The spatial smoothing kernel, however, is something you may want to change. In general, smoothing averages together signal and cancels out noise, and larger smoothing kernels can give you stronger signal. If you're looking at larger cortical regions, you may want to use a larger kernel, say around 6 millimeters or more. If instead you're more interested in smaller regions, such as the inferior frontal gyrus or the amygdala, you may want to use a smaller kernel to avoid averaging signal from functionally distinct areas. For now, I'll leave this as it is. The last processing tab is registration. Note that in the standard space field, a template brain has already been loaded, the MNI-152 brain. This is a good default to use, although you may want to change it if you're analyzing special populations, such as children. Remember that our goal is to warp or normalize the subject's anatomical image to the template. Click on the button next to Main Structural Image to expand it and see the input field. From here, if you click on the folder button, you should then select the brain-extracted anatomical image, not the original one. The 2 drop-down menus specify how much to search in order to set up a good initial alignment, and then how many degrees of freedom to use when registering and normalizing. The menus below the standard space field indicate the options to be used for normalizing the anatomical image to the template, and the menus below the main structural image field indicate the options for registering the functional images to the anatomical. Note that registration has a BBR option, which stands for Brain Boundary Registration. This is a more advanced registration technique that uses the tissue boundaries to generate a better registration. The only downside is that it takes longer. These options are up to you, but for now I'll set these to full search and 12 degrees of freedom for both. Later on, you'll do an exercise in which you'll change these options to see how they affect the results. Now click Go. This will open up an HTML page tracking the progress of the pre-processing steps. It may take around 5 to 10 minutes to finish. When one of the steps is completed, you'll see the output under the corresponding tab. When FEAT has finished pre-processing the data, click on each of the links to see what the output looks like. Since we only did pre-processing, we only have results for registration and pre-stats. Let's look at the registration results. The first image shows one of the volumes of the functional run normalized to the template you specified in FEAT. The red lines and the background image can be confusing at first, but with practice you'll be able to easily tell which is which. In this case, the grayscale image is the functional image, and the red lines trace the major anatomical features of the template. Make sure that the outlines of both brains are aligned, as well as the internal structures such as the corpus callosum and the ventricles. This image is shown first because if any of the other normalization and registration steps failed, this step would show obvious errors. Scroll down to see the other registration steps. The first one is the alignment of a representative functional image to the high-res, or anatomical image. The upper row shows a red outline of the anatomical image overlaid on the functional image, and the bottom row shows the reverse. Observe whether the outlines of the brains match up. Once you've checked those, take a look at the last two montages and see if you can figure out what they represent. Now scroll back to the top of the page and then click on the pre-stats link. These figures will show you how much the subject moved from volume to volume. There are 3 separate images, one showing the motion in rotations, one in translations, and a combined measure of all of the movements. The absolute motion is the amount of displacement from the reference volume, which in FSL is the middle volume of the time series, and relative motion is the displacement from volume to volume. So how much motion is too much? If there is relative motion of more than half a voxel size or absolute motion of more than a voxel, you may want to consider more advanced correction techniques such as scrubbing, or maybe just remove the run from the analysis altogether. So if you acquired a volume with, for example, 3 by 3 by 3 millimeter voxel resolution, you would flag any runs with relative motion of more than 1.5 millimeters from volume to volume, or absolute motion of more than 3 millimeters across the entire run. These are only guidelines, and you may decide to change them depending on the population you're studying. If both the registration and pre-stats figures look good, your pre-processing is probably okay. If you nevertheless want to inspect the images more closely, click on Fossilize. When you click on File, Add from File, you'll notice that a new directory has been created, run1.feat. FSL appends .feat to the output label to signify that it contains output from FEAT. Within this directory, there are many files and subdirectories. The logs folder contains text files reporting what was done for each pre-processing step. The MC folder contains files generated during motion correction. And finally, the reg folder contains the output from registration and normalization. The HTML files are the web pages we were looking at a few moments ago. Load the example func and filtered func data files. Overlay the example func image by clicking on the up arrow here. Example func is a representative volume from the time series. FSL's default is to choose the median volume. Filtered func data, which you can see by clicking on the eye icon here to make example func invisible, is the functional data after all the preprocessing has been applied to it. The most obvious difference is that it is blurrier than the example func image due to smoothing. Remove those images by clicking on the minus sign next to them, and then, once they've been removed, load the high-res and the example func to high-res images, which are in the reg directory. Once they've been loaded, change the max contrast if you want, and then make the example func to high-res the overlay. You can both hide and reveal it to see whether it lines up with the major anatomical features of the anatomical image, such as the central sulcus and cingulate sulcus, and internal structures such as the ventricles. The alignment may not be perfect, but it should be close. As an exercise, try the same quality check with the standard and the high-res to standard images.